In the last video, we learned a method of proof called proof by induction, and I gotta tell you right now, it's a little bit deceptive because it turns out there are three forms of proof by induction. And what we worked on in that last video was something that we call weak induction. We're gonna learn two different types of induction. This one is, well, in the textbook they call it the extended principle of induction. I would rather call it a generalization of the weak form induction that we worked on last time. You can call it whatever you want. But what we're going to do is first look at why we would even need to use a different form of induction. And in particular, we're going to look at a theorem that does not start at n equals 1. And you'll see what I mean when we get there. We will show that we can still use induction to prove it. And then we will use that to state a more general form of induction, which is going to be the extended principle of induction. All right, so here's the problem that we're going to be working on. And we're going to ask the question, which is bigger, 3 times n or 2 to the n? And we're going to look at a few different values of n to see which is which. Well, if we have n equals 1, we get 3 bigger than 2. It looks like 3n might be bigger. N equals 2. 6 is bigger than 4. Yeah, 3n still bigger. N equals 3. 9 greater than 8. I think I see a pattern for me here, except for, well, when we get to n equals 4, now 12 is less than 16. Now 3n is less than 2 to the n. N equals 5, we get 15 is less than 32. N equals 6, we get 18 is less than 64. And we can see that not only has the inequality flipped once we get to 4, but it looks like it's going to stay that way. It's going to stay that 3n is going to be less than 2 to the n, but not for the first 3, just for n at least 4. So it looks like our theorem is going to be 3n is less than 2 to the n for all n greater than or equal to 4. Which looks like a perfect theorem for proving using induction, except for one small issue. It's not true for n greater than or equal to 1. And if you remember the induction that we were looking at in the last video, the form of our theorems were always for all n greater than or equal to 1, p of n, right? And in this case, it's for all n greater than or equal to 4, p of n, where p of n is 3n is less than 2 to the n. Well, it turns out we can still use induction, right? The only difference is we're going to have a different basis step. In other words, we're going to have a different base case. So in this case, usually our basis step is at n equals 1, but to be honest, the reason we did that is because that's where our theorem started. In this case, our basis step is going to be n equals 4 because that's when our formula starts being true. So if we have n equals 4, 3n is equal to 12, 2 to the n equals 16, and therefore for n equals 4 we have 3n is less than 2 to the n. And now for the rest of the theorem, it's going to be exactly the same. We're going to do our inductive step just like we did before. And let's see how it actually works going from n equals 4 to n equals 5. So we've already done the case where n equals 4. We know that 3 times 4 is less than 2 to the 4th. Question is, how would we use that, actually use that fact to show that 3 times 5 is less than 2 to the 5th? I mean, besides just 3 times 5 is 15, 2 to the 5th is equal to 32, we're done. How would I actually use that previous case to get to the next case? We're practicing using induction. Well, let's see. I want to figure out what 3 times 5 is. How do I get 3 times 4 involved? Where I can turn that 5 into 4 times 1. I can use the distributive property, get 3 times 4 plus 3. And 3 times 4, I know by my induction hypothesis, we're assuming that 3 times 4 is less than 2 to the 4th, so I can put that in. So I get that is less than 2 to the 4th plus 3. And so if I put those together, I get that 3 times 5 is less than 2 to the 4th plus 3. Well, let's see. I know that 3 times 5 is less than 2 to the 4th plus 3, but I want it to be less than 2 to the 5th. So if somehow I could prove that 2 to the 4th plus 3 is less than 2 to the 5th, then I can use that string of inequalities to show that 3 times 5 is less than 2 to the 5th. So now I'm going to take a little time out and prove that 2 to the 4th plus 3 is less than 2 to the 5th. Well, it turns I don't know exactly how the logic is going to work, but I know I want to end up with 2 to the 4th plus 3 is less than 2 to the 5th. Let's see if I can work backwards to see if I can find out what my proof is going to look like when it goes forward. Well, let's see. So if my 2 to the 5th is 2 times 2 to the 4th. If I subtract 2 to the 4th from both sides, I get 3 is less than 2 times 2 to the 4th minus 2 to the 4th. Well, that's interesting. I have 2 times 2 to the 4th minus 1 times 2 to the 4th. That will give me 1 times 2 to the 4th. And is it true that 3 is less than 1 times 2 to the 4th? Yeah, 2 to the 4th is 16. 16 is bigger than 3. So that's how my logic is going to go. I can actually prove that's true, that 2 to the 4th plus 3 is less than 2 to the 5th, by starting with the fact 3 is less than 2 to the 4th, and 2 to the 4th is equal to 2 times 2 to the 4th minus 2 to the 4th. That will give me 2 to the 4th plus 3 is less than 2 times 2 to the 4th, and 2 to the 4th plus 3 is less than 2 to the 5th. So it looks like I can prove that induction step. Alright, so let's see how this is going to work in general, right? So my inductive step, I'm going to assume that 3 times k is less than 2 to the k, where k, and I have to assume that k is greater than or equal to 4 because that was my basis step. And I'm going to use that to show that 3 times k plus 1 is less than 2 to the k plus 1. So let's look at 3 times k plus 1. I want to use the fact that 3k is less than 2 to the k, so I probably want to use the distributive property. I get 3k plus 3. I know that 3k is less than 2 to the k, so I can substitute that in. If 3k is less than 2 to the k, that means 3k plus 3 is less than 2 to the k plus 3. So that gives me that 3 times k plus 1 is less than 2 to the k plus 3, and I'm in the same situation as I was before. If somehow I can prove that 2 to the k plus 3 is less than 2 to the k plus 1, then I can use that string of inequalities to show that 3 times k plus 1 is less than 2 to the k plus 1. So let's see how I'm going to prove it. Well, once again, I want to see if I can work my way back from what I want to prove towards what I can assume to get there. So if I look at what I want to end up with is 2 to the k plus 3 is less than 2 to the k plus 1. I can split that right-hand side into 2 times 2 to the k. I can move that 2 to the k on the left-hand side over to the right to get 3 is less than 2 times 2 to the k minus 2 to the k. And remember, that's 2 times 2 to the k minus 1 times 2 to the k. That gives me 3 is less than 1 times 2 to the k. And that is actually true. Remember, we're assuming that k is at least 4. And that means that 3 is less than 16 for sure, and 2 to the k is going to be at least 16 because k is greater than or equal to 4. So our proof is going to go, since k is greater than or equal to 4, I have 3 is less than 1 times 2 to the k, and then follow those algebraic steps down to the end where I'll get 2 to the k plus 3 is less than 2 to the k plus 1. Alright, so let's see if we can put this together into a formal proof by induction where our theorem is going to start at n equals 4. So, again for the proof, we're going to warn our reader that we're going to prove this by induction. Since we are proving our theorem that is valid for n greater than or equal to 4, the basis step is going to be n equals 4. It's nice to tell your reader what the basis step is, especially since, at least at the beginning, we're not assuming that our reader is very comfortable with this new form of induction. So we're telling them what the basis step is. So for this, we just plug in n equals 4. We get 3n equals 12, 2 to the n equals 16, 12 is less than 16, and therefore 3n is less than 2 to the n in this case. So that's our basis step. Now, for the inductive step, we're going to assume that the theorem is true for some n equals k, where k is greater than or equal to 4, and then prove the theorem for n equals k plus 1. So we're going to assume that 3k is less than 2 to the k, and show that 3 times k plus 1 is less than 2 to the k plus 1. And let's see if we can use our scratch work from the previous slides to get us there. So right now, remember the sort of linchpin of our proof was trying to prove that 2 to the k plus 3 was less than 2 to the k plus 1. And so we're sort of taking a detour in the proof, so we're sort of telling our reader, look, we're going to get back to the main part of the proof, I promise, but right now we need to show that 2 to the k plus 3 is less than 2 to the k plus 1. That is fine to do as long as you are nice to your reader about it. So remember, we kind of worked our way backwards when we were doing our scratch work, but the starting point was the fact that since k is greater than or equal to 4, we have 2 to the k is greater than or equal to 16. And that was our starting point. And so that means 3 is less than 2 to the k. If 2 to the k is at least 16, 16 is bigger than 3, that means 3 is less than 2 to the k. And then we're going to use that inequality to get what we want. So remember, we're going to write 2 to the k equals 2 times 2 to the k minus 1 times 2 to the k, and then substitute that in. So we have 3 is less than 2 times 2 to the k minus 2 to the k. Then we're going to rewrite 2 times 2 to the k as 2 to the k plus 1, which gives us that 3 is less than 2 to the k plus 1 minus 2 to the k. And then we're going to bring that 2 to the k over to the left-hand side to get 2 to the k plus 3 is less than 2 to the k plus 1. Now we're going to finally get back to proving that 3 times k plus 1 is less than 2 to the k plus 1, which remember, that was our goal to begin with. So here's what we have. 3 times k plus 1 is equal to 3k plus 3. By our induction hypothesis, we know that 3k is less than 2 to the k, and that means that 3k plus 3 is less than 2 to the k plus 3. Again, we're replacing 3k with a quantity that's bigger than 3k. That means that 3 times k plus 1 is less than 2 to the k plus 3. But remember, we showed that 2 to the k plus 3 is less than 2 to the k plus 1. And that means that 3 to the k plus 1 is also less than 2 to the k plus 1. Again, 3 times k plus 1 is smaller than 2 to the k plus 3. 2 to the k plus 3 is even smaller than 2 to the k plus 1. Putting those together, we have to have 3 times k plus 1 is less than 2 to the k plus 1. And that completes our inductive step, which completes our proof. All right, so in general, if we want to prove a statement that looks like for all n greater than or equal to m, some p of n, where p of n is some open sentence, our basis step is prove the theorem for n equals m. In other words, prove p of m. The induction step is assume that the theorem is true for n equals k, where k is at least m. In other words, assume p of k. And then you're going to show the theorem is true for n equals k plus 1. In other words, we're going to show p of k plus 1. All right, so now you're in a good position to work on the first activity for strong induction. For the second one, you're going to probably want to look at the next video.